Okay, this is sample problem 14.3. The gas phase reaction of nitric oxide with hydrogen at 1,280 degrees Celsius is 2NO gas plus 2H2 gas forms N2 gas plus 2H2O gas. From the following data collected at 1,280 degrees C, determine A, the rate law, B, the rate constant, including units, and C, the rate of reaction when concentration of NO is equal to 4.8 times 10 to the minus 3 molar, and the concentration of H2 is equal to 6.2 times 10 to the minus 3 molar, given 3 sets of data. So look at this problem at the bottom. It tells you there are 3 experiments being performed. So we're not going to go into the details of how these experiments are formed. We will do that later. But imagine you've just got some flask, a pot, and you're doing some reaction in there, and you got a stopwatch, and you're measuring how fast the reaction is occurring. Imagine it changes color after some period of time. And then imagine that you change something about the reaction and do it a second time. And then you change it again, and you do it a third time. So you're doing the experiment 3 different times, and you have 3 sets of data. The way the numbers are set up is they're numbered in terms of experiments, 1, 2, 3. The variables, there's 3 variables here. 2 of them are what we call independent variables. The independent variables are the ones that you change that cause something else to change. So they're changing the concentration of NO in the units of molarity, and they're changing the concentration of H2 in the units of molarity. Those are those second and third columns, the ones with the scientific notation numbers. The 4th column is the dependent variable, which is the rate. Now, it says initial rate because that's a technical term that means we're measuring how fast the reaction is occurring right at the beginning of the reaction. But that doesn't matter for us. It's the same rate as we talked about in the previous section and in the previous problems. It's the speed of the reaction. Now look at the numbers. For experiment 1, the initial rate is 1.3 times 10 to the minus 5 molarity per second. For experiment 2, it's a larger number. It's gone up. Compare the rate for experiment 2 to rate 1, the rate for experiment 1. Notice, convince yourself that the second number is bigger than the first one. 5.0 times 10 to the negative 5 is greater than 1.3 times 10 to the minus 5. So the speed is greater. That second experiment is faster. Imagine it just like the speed of someone running. If someone is running at 1.3 versus running at 5.0, the person running at 5.0 is running faster than the person running at 1.3. So something has made that second experiment, the reaction, go faster than the first experiment. What could it be? Well, all these experiments are done at the same temperature. So it can't be temperature. There's no other information given except the initial concentrations. These concentrations are not the same in both of those experiments. In the first experiment, the concentration of NO is smaller. It's less than it is for experiment 2. It's 5.0 times 10 to the minus 3. That's 0.005. But in the second experiment, it's 1.0 times 10 to the negative 2. That's 0.01. That's greater than experiment 1. Don't trick yourself into thinking, oh, 5 is more than 1, so 1 is faster or bigger. It's not, because it's got times 10 to the minus 3. The second concentration, H2, is the same. right? It doesn't change. It's 2.0 times 10 to the minus 3 for both of them. So the difference here, what's causing the rate to increase for experiment 2 over experiment 1 is the concentration of NO is greater in experiment 2. And you can look at experiment 3 and convince yourself of the same thing. As the concentration of the reactant increases, the speed increases. That's the sort of the take-home message of those numbers. But what we want to do is we want to find what's called the rate law. The rate law looks like this. R for rate. Oops, let me put a better pen in here. The rate is equal to a constant, which is called the rate constant, lowercase k. All right? That's just a constant. You don't need to worry about what it is until we do the calculation with it. Times the concentration of the first reactant. The first reactant is NO. And then you're going to raise that to, you have a choice. It could be an X or it could be an M. People, different books, different authors will use different variables for this. I'm going to stay consistent with what your textbook uses, which is to put an X. So we don't know what X is, just like we don't know what K is. Times the concentration of the second reactant, which is H2, to the Y. We're just using XY. If we had 3 reactants, we would do XYZ. Now, unlike expressions, rate laws are generally written only in terms of the reactants, generally. Okay? So just for now, do it only in terms of the reactants. Don't worry about the products. That's called the rate law. Not the rate expression. Don't get confused with that term. That was used in section 1. It's called the rate law. X and Y are unknown. So what's X? What's Y? What's K? We don't know what they are. We're going to try to figure out what they are. That's the whole idea of this problem. So when they say find the rate law, really what they're trying to do is they're saying, tell us what X is, tell us what Y is, and tell us what K is with units. All right? So here's one way to do it. It's the most standard method of analysis for this type of problem. You pick 2 experiments, which one of the reactants is changing concentration, but the other one is not. So just looking at the numbers, experiment 2 and experiment 1 have different concentrations of NO, but they have the same concentrations of H2. That's exactly what we want. We want to have one reactant changing concentrations, but not the other, not both of them. If both of them are changing, that makes it difficult. So I'm going to take the following analysis. What you do is you write R2, meaning what's the rate for experiment 2, is equal to 5.0 times 10 to the minus 5 molarity per second, right? I'm just taking the number all the way over at the right. And then I'm going to divide that by R1. And I'm not going to tell you why I'm doing that yet, but you'll see what's going on. We're going to divide this by R1. Well, R1 is 1.3 times 10 to the minus 5. Now, you could do R2 over R1 or R1 over R2. Take the one that's larger and divide it by the one that's smaller. So R2 over R1. Don't do R1 over R2. You can if you want to play little math games, but in general, you want to use the one in the top. The one in the numerator should be the one which is a larger number. Now, 5.0 divided by 1.3 is 3.846. I don't know why they picked such numbers. That's unitless though, right? Because the units are going to cancel. Now, the rate law says that R is equal to K times the concentration of NO. So for experiment 2, the concentration of NO is 1.0 times 10 to the negative 2, and then that's raised to the X. We don't know what X is. Times the concentration of H2. Where am I getting this? I'm getting it here, and then I'm looking at the numbers up above. 2.0 times 10 to the minus 3. And then that's raised to the Y. I left the units out of there just to kind of make this a little bit easier to look at to the eye. Otherwise, it gets so busy in here. And then I'm going to do experiment 1, right? So experiment 1 is 5.0, okay, times 5.0 times 10 to the minus 3 to the x, 2.0 times 10 to the minus 3 to the y, right? So what I'm doing is I'm saying every experiment has the same rate law. It's going to be the same. The only thing that's going to be different are the actual concentrations. That's the only thing that will be different. So I'm making sure, be careful when you do these problems. It's very easy to get the numbers mixed up. There's a lot of scientific notation, lots of zeros and negatives and stuff. Make sure you check. I'm doing R2 over R1, okay? So I'm using the concentrations in that data set, in that table. Now what I'm going to do is I'm going to cancel everything that's the same. K and K is the same. This number is the same as that number. Y is the same as Y. So that ratio is 1. So that means that 3.846 is equal to this divided by this, right? Now what is that equal to? Well, that's a little tricky because you got these x's. Those are exponents, and we don't know if the exponent is a 1 or a 2 or a 7 or a pi. So here's what we can say. If you have a number and it's raised to a exponent, and that's divided by a number raised to the same exponent, you can write it as the ratio of the numerator to the denominator to the same exponent x. That's one thing you can do. That allows you to do the division within the parentheses. So 1.0 times 10 to the minus 3 divided by 5.0 times 10 to the minus 3. It looks like that's a 2, right? That's 0.01 divided by 0.005, so that's 2. So that means that 3.846 is equal to 2 to the x. Okay? Now that's kind of interesting when you look at that, because what we want to do at this stage is we want to figure out what that's going to work out to. Okay? So here's what I'm going to do. I'm going to ask myself, let's let x equal 0. So if I let x equal 0, so let x equal 0, we would have 2 to the 0. Now you may or may not remember from algebra that a number, other than 0, raised to the 0th power is equal to 1. So what you do is you ask yourself, is 1 equal to 3.846? And the answer is no, it can't be. So we know x is not 0. So then we try the next number. We say 2 raised to the 1. We let x equal 1. Well, 2 to the 1 is equal to 2. 3.846 is certainly not equal to 2, so that's no good. So that means that x is not equal to 1. So then we do the last one, which is we say 2 raised to the 2. We let x equal 2. We're going to leave behind any possibilities of x being 1.7 or anything like that. We're just going to do whole numbers, so 2. 2 to the 2 is 4. Well, 4 is pretty darn close to 3.846. So what I'm going to do is I'm going to say that it looks like the closest possible value is x equals 2. So now what I'm going to do is I'm going to come back up to here, and I am going to put in a 2 there. We just figured out that x is equal to 2. Okay? So that is a third of the way done. We're getting close to finishing out what this rate law is. To get the rate law, we need to know what k, x, and y are. So we know what x is. Now we do the same thing for y. We now find 2 reactions, 2 experiments, where the other reactant is changing, but not the other one that we just looked at. So we just saw the case where NO was changing concentrations, experiment 2 and experiment 1. Now look for 2 experiments where H2 is changing concentrations. Now you have a couple choices. You could do 1 and 3, or you could do 2 and 3. And The problem with doing 1 and 3, it's not an insurmountable problem, but it is a problem, is that the problem with doing 1 and 3 is that NO is changing also. You want to have it where only H2 is changing. So that would be 2 and 3. For 2 and 3, H2 is changing, but NO is not. So again, do the larger one divided by the smaller one. So I'm going to take R3 over R2. So that would be K. Now, we're doing 3, so that would be 1.0 times 10 to the minus 2 to the x. Why did I get a little, it's funny, I had a square bracket at the beginning, and then I changed it to a rounded bracket there, so I don't need to do that. Technically, I just need to use, I can use a rounded one, since we know what the value is. Okay, so 1.0 times 10 to the minus 2 times x, and then times 4.0 times 10 to the minus 3. Do the same thing, divide that by R2. So R2 is 1.0 times 10 to the minus 2 to the x. Oh, by the way, sorry, this is a y. Divided by 2.0 times 10 to the minus 3. You have to be really careful. It's so easy, your eyes, to just lose track of what numbers you're looking for. So it's not a bad idea after each step, particularly when you're learning how to do it, just check your numbers. Make sure you're doing what you're thinking you're doing. I'm trying to take rate 3 over rate 2. So I want k times, rate 3 would be 1.0 times 10 to the minus 2 to the x, good. 4.0 times 10 to the minus 3 to the y, good. And then divided by k, divided by 1.0 times 10 to the minus 2 to the x, 2.0 times 10 to the minus 3 to the y. Good. Looks like it's there. Now, this stuff right here is getting in the way, so let's get rid of it. We don't need to keep it in here anymore. Now, what we can do is we can also say, well, wait a minute, what is that equal to? Well, that's equal to the numbers, the rates. So R3 is 1.0 times 10 to the minus 4 divided by 5.0 times 10 to the minus 5. Why am I doing that? That's what I did over here. I did it there. I had to get that ratio to get 3.846. I'm doing the same thing here. Now this one, 1.0 times 10 to the minus 4 over 5 times 10 to the minus 5, that's just 2. That's equal to 2. So it didn't come out to like 2.178 or anything like that, like the 3.846 did. This one just came out to a nice whole number, 2. Sometimes that happens. So 2, that ratio, is equal to k over k. We can get rid of that. Get over that. That's the same. And then again, these are both to the same exponent, so it's equal to 4.0 times 10 to the minus 3 over 2.0 times 10 to the minus 3 to the y. And that's now equal to 2. Well, if you do that ratio, you get 2 to the y. That's equal to 2. So we would do the same test. 2 to the 0. Well, that's equal to 1. Then 1 is not equal to 2. 2 to the 1, that's equal to, there you go. We now know that y is equal to 1, right? 2 to the 1 is equal to 2. So now we can come back and we can make this a 1. Okay. So we're almost there. Now we just got to figure out what k is. K is not that hard to figure out. Okay, I'm going to get rid of some of this here. Okay, how do we figure out what k is? Well, we know the exponents. X is 2 and y is 1. That makes it easier. So now what I'm going to do is I'm just going to say experiment 1. You could do any of these experiments. I'm just going to pick one. Technically, we would do them all and then take the average, but I'm just going to take one of them because this is just a homework problem. It's not a real experiment you're doing in the laboratory that you're publishing an article in. So what I'm going to do is I'm going to say for experiment 1, the rate is 1.3 times 10 to the minus 5. You know what? I'm going to actually come down here. We do not have enough room there, and I don't want to take a half hour to erase this. Okay? So let's try it this way. The rate is equal to 1.3 times 10 to the minus 5. For now, I'm going to put the units in. We do need to find the units for this particular step. Okay, so again, I'm just picking one of the experiments. You could do 2, you could do 3. We're trying to find K. That is equal to K times the concentration of NO. For experiment 1, that's 5.0 times 10 to the minus 3 molar. So 5.0 times 10 to the minus 3 molar. Squared, right? Don't forget you got that 2. That was all that work we did at the beginning. We got a 2 there. Times the concentration of H2, which is 2.0 times 10 to the minus 3. That was to a 1, so I'm not going to put any exponent there. Okay? Now, even though you have all this scientific notation and units and exponents in there, this is a simple problem to solve. Because really what you have is a number. So let me make it kind of give you an analogy. Suppose I said 6 equals K times 3 times 1. Solve for K. What you would do is you would divide both sides by 3 and both sides by 1. Right, and that would give you K. Do the same thing here. We divide both sides by 5.0 times 10 to the minus 3 molar squared, and then we would divide it by 2.0 times 10 to the minus 3 molar. So I'm going to do that. So I'm going to say 1.3 times 10 to the minus 5 molarity per second. Now I need a lot of room here because I got all these numbers over here on the right side that I'm going to divide by. Furthermore, I've got units, and you want to leave the units in for this step. You've also got exponents. Don't forget the exponents. That is equal to K. All right? That big mess there, right? So let's go through the arithmetic. You can use your calculator if you want. You can do it in your head if you want, whatever. 1.3 times 10 to the minus 5 divided by 5 times 10 to the minus 3. But you gotta do 5 times 10 to the minus 3 twice, right? And then you gotta divide it by 2 times 10 to the minus 3. And so it looks like you get 260. I'm pretty sure that's right. So if you don't get 260, check your calculations again. Remember, you got to square this one and you got to divide by both of them. What about the units? Oh, the units are complicated here because you have exponents and you've got multiple units that are the same, but it doesn't matter. Here's what I'm going to do. I'm going to break out the units separately. In the numerator, we have molarity over seconds. In the denominator, we have molarity squared. Whatever you do to the number, you do the same thing to the units. So molarity squared. And then here we have molarity, so times molarity. Oh, molarity squared times molarity, that's molarity cubed. Or, if you're clever about it, molarity over molarity is 1. That way you don't have to worry about multiplying molarity squared times molarity. So now you get something weird. There's nothing in the top. What is it? If there's no units at all, we just put a 1. And then that's divided by molarity squared. Now this is really awkward looking. It's really saying per second per molarity squared. It's ungainly. Unfortunately, with rate laws, that's just the way these things work. The rate constants sometimes have unintuitive units, but we can clean it up and make it look pretty. So it makes it look like we know what we're doing. So here's how we do that. If you have 1 over 2, that's equal to 2 to the minus 1. If you have 1 over seconds, that's seconds to the minus 1. So it's not uncommon to write it this way. If you have 1 over molarity squared, that could be written as molarity to the minus 2. So here's what I'm going to do. I'm going to write this as molarity minus 2 times seconds minus 1. Crazy looking, but cool looking. Not that intuitive. What it essentially says is the rate constant is such a value that the molarity squared is changing per second. 1 over the molarity squared is changing per second. So it's very odd. It's just the units that make things work out. And keep in mind that those units depend on those exponents that you did in the first part. If this exponent had been a 1 instead of a 2, or this one had been a 2 instead of a 1, that would change what's going on in terms of the units, all through the algebra of units, okay? Now, we have one more step here. By the way, we would now claim that we have elucidated or determined the rate law. The rate law, we would say, is now 260 molarity minus 2 seconds minus 1 times the concentration of NO to the second power times the concentration of H2 to the first. That would be called the rate law. Typically, that's what you would say. Oh, now we know the rate law. It's 260 molarity minus 2 seconds minus 1 times the concentration of NO squared times the concentration of H2. But there is one more question they ask in here. They say, hey, what is the rate of the reaction if the concentration of NO is 4.8 times 10 to the minus 3 molar, and the concentration of H2 is 6.2 times 10 to the minus 3 molar, 4.8 and 6.2. So here's all you got to do for that. Yeah, you just take your number there. We already know what K is. And then you put in, what is it, 4.8? 4.8 times 10 to the minus 3. Squared. Remember, it's squared. You got that second power there. Times 6.2 times 10 to the minus 3. Okay. Now, go through the arithmetic there. 260. Do the numbers separately. 260 times 4.8 times 10 to the minus 3. But you got to square that, right? Times 4.8 times 10 to the minus 3. And then you got to multiply that by 6.2 times 10 to the minus 3. And you get this really small number. You get 3.71, I think it is. Yeah, 3.71. I'm going to round it to 3.71. Times 10 to the minus 5. What about the units? Rate should be molarity per second, but we can show that it's the case. Molarity to the second power there divided by molarity to the second power. So those molarities cancel. And then you got seconds, so divided by seconds. So you could write it this way, s to the minus 1. We still have molarity. So molarity times seconds to the minus 1. That's often how people will write it. But it wouldn't be incorrect to write it this way either. Molarity per second, because that's what seconds to the minus 1 means. And there you go. So that we run through the whole thing. We figured out what those what the exponents were. Once we knew the exponents, I picked one of the experiments. You could pick 1, 2, or 3, or all of them if you want to do them all and take the average. That allowed you to do algebraically figure out what the value K was. Once you figured out what K was, now if they give you the concentrations, you can use the value of K that you figured out and the rate law to figure out how fast the reaction is going to be. 3.7 times 10 to the minus 5 is sort of in between, right? Well, it's in between experiment 1 and experiment 2, right? Experiment 1 is 1.3 times 10 to the minus 5. Experiment 2 is 5 times 10 to the minus 5. 3.7 times 10 to the minus 5 is right in between there.